Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 51. In this lecture, we'll discuss the Carnot engine. This topic is covered in Chapter 22 of our textbook by Surway and Jewett. In our previous lecture, we discussed heat engines and heat pumps in quite a bit of detail. In this lecture, we want to explore the idea of maximum efficiency or performance for any such device. So we want to know the maximum efficiency or performance that is achievable by the optimal thermodynamic cycle. A little more precisely, this is the question we want to explore in this lecture. Given two heat reservoirs at temperatures TH and TC, what is the maximum efficiency or performance that a heat engine or heat pump can achieve? So we're assuming we have two heat reservoirs. One of them is relatively hot, the other one's relatively cold, and their temperatures are fixed, and we have some working substance going through some thermodynamic cycle. Assuming the thermodynamic cycle is optimal, what is the best case scenario or maximum efficiency that we can achieve? Let's review some facts about heat engines and heat pumps. Recall that in a heat engine, thermal energy flows from something hot to something cold, and as a result, we have an output of work. This output of work is the thing that we want to maximize. This output of work is the useful stuff that a heat engine gives us. The output of work is what we use to move a car or a steam engine forward. The output of work is what we use to rotate an electric generator, for example, to generate electricity. In the case of a heat pump, all the arrows are reversed in direction. So thermal energy flows in the opposite direction that it normally would spontaneously flow. So we describe the situation by saying that in a heat pump, thermal energy flows upstream. In order to achieve this particular flow of thermal energy from something cold to something hot, we need an input of work. This input of work is the thing that we want to minimize. This input of work is the thing that costs us money in most cases, so we like to input the input of work to be a minimum value. We've defined the following quantities to characterize the performance of these devices. For a heat engine, we usually talk about the efficiency, and the efficiency is defined as W divided by QH. For a heat pump, we talk about the coefficient of performance in cooling mode or in heating mode. Recall that a coefficient of performance is basically very similar to efficiency. It essentially tells us how good or bad the device is. The main difference is that efficiency runs from 0 to 1, whereas coefficient of performance runs from 0 to infinity. The coefficients of performance in cooling mode and heating mode are defined as follows. So in this lecture, what we want to find out is what are the optimal values of these three parameters for the optimal thermodynamic cycle. The question of maximum efficiency was investigated by Nicolas Carnot. Carnot was a young French military engineer and physicist. He died at the age of 36 in a cholera epidemic, but in his short life, he managed to discover the most efficient thermodynamic cycle. And today, any engine that uses that cycle is referred to as a Carnot engine. Carnot discovered that the most efficient thermodynamic cycle uses four fundamental thermodynamic processes. The first step of the Carnot cycle consists of an isothermal compression of the working substance. So if the working substance is a gas, like steam, for example, we must begin by a compression of that gas. For this step, we need a cold reservoir so that energy can be transferred out of the gas and into the cold reservoir, thereby compressing the gas to a smaller volume. The second step of the Carnot cycle is an adiabatic compression. Remember, an adiabatic process is one in which heat is zero, so there's no transfer of thermal energy in or out of the system. Therefore, for this step, we need to thermally isolate the gas so that thermal energy cannot flow in or out. The third step is an isothermal expansion. For this step, we need a hot reservoir. So we need another substance that is relatively hot when compared to the gas. We can then transfer thermal energy from the hot reservoir into the gas, causing it to expand. The fourth step of the Carnot cycle is an adiabatic expansion. Here, the volume of the gas increases, but it does so in thermal isolation. The proof that these four steps give us the most efficient thermodynamic cycle requires the use of the second law of thermodynamics. We have not yet discussed the second law of thermodynamics. In fact, we'll discuss the second law in our next lecture. However, we will not prove that the Carnot cycle is in fact the most efficient cycle. For us, what's important are some basic properties of the Carnot cycle, and in particular, we'd like to know what the efficiency of the Carnot engine is. Knowing the efficiency of the Carnot engine gives us a useful upper bound for any other practical engine that one might construct. So let's delve a little deeper into the Carnot cycle. The Carnot cycle for a specific sample of gas is shown here on this PV diagram by this closed graph. Recall that the first step of the Carnot cycle is an isothermal compression. For this step, we need a cold reservoir. So we need something whose temperature is relatively low compared to the gas itself. We'll place the gas in contact with this cold reservoir, and therefore thermal energy will leave the gas and enter the reservoir. Since thermal energy is leaving the gas, we say that Q in this step is negative. At the same time, a piston compresses the gas, so the piston is pushing down on the gas, reducing its volume, and therefore doing positive work. In an isothermal process, the initial temperature and the final temperature are equal to each other. Therefore, by the equipartition theorem, delta E is equal to 0. This also tells us that the absolute value of W must equal to the absolute value of Q, because by the first law of thermodynamics, delta E is equal to W plus Q. The second step of the Carnot cycle is another compression. This time it's an adiabatic compression. So the volume of the gas continues to be reduced, but this time adiabatically. So by definition, Q is equal to 0. The gas is thermally isolated. Energy is not allowed to enter or leave through heat. However, the piston continues to compress the gas. So the piston continues to reduce the volume of the gas, and therefore it performs positive work. According to the first law of thermodynamics, delta E is equal to W plus Q. Therefore, in this case, delta E is positive, meaning that the thermal or internal energy of the system increases in this second step. The third step is an isothermal expansion. Now the volume of the gas begins to increase. To achieve this step, we need to place the gas in contact with something that is relatively warm. This is the hot reservoir. Thermal energy now leaves the hot reservoir and enters the system. Since this is an input of thermal energy, we say Q is positive. At the same time, we allow the piston to move upwards. The volume of the gas increases, so the gas is performing work, but the work is now negative. Since this is an isothermal process, the initial temperature and the final temperature are equal to each other, and by the equipartition theorem, delta E must be equal to 0. So we can say W plus Q must equal to 0 for this step. The final step of the Carnot cycle is another expansion, this time an adiabatic expansion. So the volume continues to grow, but this time we have thermally isolated the gas. We're not allowing heat to enter or leave the system. However, we allow the piston to continue to expand. As the volume increases, the gas performs work, but once again, the work is negative. By the first law of thermodynamics, delta E must equal to Q plus W. So in this case, delta E is negative, meaning that the internal energy of the system is going to decrease. Now notice that in this particular example, I've gone around the cycle in the clockwise direction. So we think of the area inside as negative work, and we would describe this device as a heat engine, specifically a Carnot engine. However, each one of these steps could be reversed, so we could actually go around the cycle in the counterclockwise direction. In that case, we would have a Carnot heat pump. In either case, given a specific hot reservoir and a specific cold reservoir, this is the most efficient thermodynamic cycle that one could achieve. Probably the most important characteristic of a Carnot cycle is its efficiency. As I've mentioned already, the efficiency of a Carnot cycle gives us a useful upper bound for the efficiency of any other thermodynamic cycle that you might want to construct. To calculate the efficiency of a Carnot cycle, the first fact that we will need is the following. The amount of thermal energy that leaves the system and enters the cold reservoir divided by the amount of energy that enters the system from the hot reservoir is equal to the temperature of the cold reservoir divided by the temperature of the hot reservoir. I did not prove this fact to you, but it should seem plausible. In general, the colder the cold reservoir is, the more energy we can pull out of the system and transfer into the cold reservoir. Similarly, the hotter the hot reservoir is, the more energy we can transfer into the system. If you are interested, a proof of this equation does appear in your textbook. However, in my opinion, the proof is not very illuminating. For us here, what's most important is how to use this equation to calculate the efficiency of a Carnot cycle. Let's start with a Carnot engine. In general, for an engine, the efficiency is defined as work divided by QH. Conservation of energy and the first law of thermodynamics tell us that the work must equal to QH minus QC. This fraction can now be written as 1 minus QC over QH. Now, these equations are true for all heat engines, but for Carnot engines specifically, we know that QC divided by QH is equal to TC divided by TH. Therefore, for a Carnot cycle used in a Carnot engine, we can say that the Carnot efficiency is equal to 1 minus TC over TH. This important equation tells us that the efficiency of the Carnot cycle depends on the two temperatures of the two reservoirs. In general, you can improve the efficiency of the Carnot engine by lowering the temperature of the cold reservoir and increasing the temperature of the hot reservoir. You can see that in the limit as TC approaches 0 and TH approaches infinity, the efficiency of a Carnot engine approaches 1 or 100%. We can apply a similar logic to a Carnot pump. In general, the coefficient of performance for a pump that is operated in cooling mode is defined as QC over W. Once again, we can write W as QH minus QC. We can then write this ratio as 1 divided by QH over QC minus 1. Now, this is true in general for any heat pump operating in cooling mode, but for a Carnot pump specifically, QC over QH is TC over TH. We can substitute this equation in here and find that the coefficient of performance for a Carnot pump used in cooling mode is equal to TC over TH minus TC. Similarly, for a heat pump operated in heating mode, we can say that the COP is equal to 1 over 1 minus QC over QH. Using the fact that QC over QH is TC over TH for a Carnot cycle, we can say that the coefficient of performance for a Carnot pump operated in heating mode is equal to TH over TH minus TC. Let's end this lecture with a practice problem. An inventor is soliciting a large financial investment from you so that he may develop an ultra-efficient steam engine which burns jet fuel at 950 Celsius to convert water to steam. The excess heat is rejected to the environment at 25 Celsius. He claims his engine has an efficiency of 78%. Will you invest? Now, without knowing the details of this heat engine, without knowing exactly what kind of a thermodynamic cycle this inventor plans to use, we cannot really calculate the efficiency of his heat engine. However, we know that whatever the efficiency is, it must be lower than the efficiency of a similar Carnot engine. So let's calculate the efficiency of a similar Carnot engine. We know that a Carnot engine must operate between a hot reservoir and a cold reservoir. In this case, we're burning jet fuel at 950 Celsius. So that's the temperature of the hot reservoir. Thermal energy is going to enter the working substance, we'll get an output of work, and some thermal energy will then be rejected or output to a cold reservoir. In this case, the cold reservoir is the environment at 25 Celsius. So now imagine you have a Carnot cycle operating between the same high and low temperatures. We know that the efficiency of a Carnot engine is equal to 1 minus Tc over Th. These temperatures should be in Kelvin, so we need to convert these temperatures from Celsius to Kelvin. 950 Celsius is equal to 1223.15 Kelvin, and 25 Celsius is equal to 298.15 Kelvin. Plugging these numbers into our calculator, we find that the efficiency of a similar Carnot engine would be 75.6%. The claimed efficiency by the inventor is higher than the Carnot efficiency, so there must be something wrong with this proposal. I don't know about you, but if this were my money, I would not invest it with this particular inventor. It's interesting to point out that the efficiency of a Carnot engine does depend on the temperatures of the cold reservoir and the hot reservoir. In this particular case, we don't have much control over the temperature of the hot reservoir. If we are going to use jet fuel, then jet fuel has a very specific burning temperature, which is fixed at 950 Celsius. However, we can imagine operating this particular engine in a colder environment. For example, if you plan to operate this particular engine at the North Pole, then the environmental temperature might be much lower than 25 degrees Celsius. You can check for yourself, but if we lower Tc to minus 4.1 degrees Celsius, then the efficiency of the Carnot engine can be improved to 78%. Nonetheless, I think the claims of this inventor are not very plausible, so I still think this is a bad investment. And that is the end of this lecture. Thank you for your attention.